A very good afternoon to all of you, my dear students. I welcome you all for this online platform of hydraulic machine, fourth semester section A. In the previous lecture, we have seen two numericals based on the reaction turbine, that is for the Francis turbine, inward flow reaction turbine, right? The numerical, we have completed the first problem number one and problem number two. I hope everyone is able to understand the numerical. If you have any doubts or any confusion, so at the end of this today's lecture, I will share you the yesterday's recording of the lecture. Okay, so no issue, so that your any type of doubts may be cleared. Okay, yes. So now we can just for a third numerical. Okay, yes, the third problem number three based on the Francis turbine. So shall we start? Okay. A Francis turbine with an overall efficiency of 75% is required to produce of 148.25 kilowatt power. It is working under a head of 7.62 meter. The peripheral velocity is equals to 0.26 into under root of 2gh, and the radial velocity of the flow at the inlet is 0.96 into under root of 2gh. The wheel runs at 150 rpm and the hydraulic losses in the turbine are 22% of the available energy. Assuming the radial discharge, determine first one the guide blade angle, second the wheel vane angle at inlet, third determine diameter of the wheel at the inlet, and fourth one is the width of the wheel at the inlet. Okay, so this one is the third numerical for the third unit of the reaction turbine. In the previous lecture, we have seen the two numericals of the inward reaction reaction turbine. Okay, so this is the numerical totally purely based on the Francis turbine. Okay, what this numerical says: a Francis turbine with an overall efficiency. Overall efficiency, that is overall efficiency, as we know that indicated by efficiency in 34. Okay, that the overall efficiency 75% is required to produce 148.25 kilowatt of power. In this, how much amount of the power it will be produced by that Francis turbine is given. Obviously, that the output power is nothing but the shaft power, right? There are the two power. So efficiency, if I'm talking about the efficiency, that the overall efficiency is nothing but the shaft power upon water power. Shaft power is nothing but the output, and the water power is nothing but the input. How much amount of water power is required to supply that turbine? Okay, that is called the input power, right? So this will be the output power that's called as the shaft power is 148.25 kilowatt power is given. Then it is working under the head of 7.62 meter. So it is in this numerical they already gives us a capital head. Okay, that is called the net head. Capital H is equals to 7.62 meter. Okay, how much amount of the height is to be get achieved by that Francis turbine? They use this in this numerical. Okay, the peripheral velocity is 0.26 into under root of 2gh. As we know that what is meant by the peripheral velocity? The peripheral velocity is the velocity of the wheel. Okay, whatever the u1 and u2 at the inlet and that outlet. So the peripheral velocity is denoted by the u1 at the inlet here, because they use us the peripheral velocity 0.26 under root of 2gs in terms of the formula. They use us the equation what in terms of the under root of 2gs, as we know that however any type of velocity can be calculated by this formula under root of 2gs, but multiplied by 0.26 is the coefficient. Okay, so the coefficient already given in this numerical. And the radial velocity of flow, what is this radial velocity of the flow is nothing but the vf1, right? Because as we know that it is a Francis turbine, radial flow means nothing but whatever the radial flow of the inlet and the outlet is the axial flow. Okay, so that will be the radial flow at the inlet is nothing but at the inlet both the is given in the numerical. So this peripheral velocity at the inlet and the radial velocity of the flow at inlet. Okay, so this will be the u1 and vf1. So the v1 u1 and vf1 is already used in terms of equation. Okay, so after that, the wheel runs at the 150 rpm. So whatever the velocity, or sorry, in terms of the speed of the wheel is given, that is a revolution per minute is 150 rpm. Okay, and the hydraulic loss in the turbine are 22% of the available energy. So in this numerical, it uses the losses. So if the whenever these losses are available, that means your condition is now at actual condition, right? because as we are already told you in the previous lecture, so any type of the turbine is work under the two condition. One is the actual condition and other is the ideal condition. So this will be the losses is given in this numerical. That means this turbine is work on a actual condition now. Okay. So the actual condition, if there is any type of the losses is available, so whatever the efficiency we have to consider the losses at the outlet. Okay. So the losses are given at the 22% of the available energy. Okay. So 22% of available energy means whatever the output is at 100% minus 22. That is for available energy. Okay. Assuming radial direct discharge. Obviously, the Francis turbine is having the radial discharge, as we know well. So the radial discharge means what? The beta is outlet. Doing discharge means what? The outlet. Outlet is nothing but the radial. It is a radial condition. That means what is the value for the B? The guide blade angle at the outlet is beta equals to 90 degree. Whenever we say that the discharge is at the outlet is radial, that means the beta is the guide blade angle at the outlet is 90 degree. Then and only we know that if it is beta equals to 90 degree, then VWT equals to what? 0 and VF1 equals to V2, right? तो द कंडीशन एज वी नो, हमें कंडीशन समझ में आनी चाहिए जैसे ही न्यूमेरिकल पढ़ते हैं कि उनको उन्होंने क्या कंडीशन दी है न्यूमेरिकल में वो समझ में आने चाहिए, वैसे ही हम उसको प्रॉब्लम को स्टार्ट कर सकते हैं, लिख सकते हैं. ओके, व्हाट दे आस्क इन देयर माइंड, फर्स्ट वन दे वांट टू नो द वैल्यू फॉर द गाइड ब्लेड एंगल. What the guide blade angle as we are available, it is a radial discharge, that means for the inlet, right? So obviously that guide blade angle means they want to know the alpha, that is called the guide blade angle at the inlet section, inlet triangle. Okay. Then the second one is the wheel vane angle at the inlet. Obviously the wheel vane angle means what? The theta. Theta is known that the angle of tip or the vane angle. Okay. So the next one is the theta. Then third one, what they want, the diameter of the wheel at the inlet. Diameter means that the diameter of the wheel at the inlet. Inlet means that D1. Okay. Whatever the diameter is available, as we know that the inlet is the D1 and then the width of the wheel at the inlet is D1. Okay. So they may means what? They want to know the dimensions of the at the inlet. Means the dimensions means in terms of the diameter and the width of the wheel at the inlet. Okay. So the D1 and D1 they want. Okay. I hope everyone is able to understand this numerical what is अवेलेबल इन योर स्क्रीन. ओके. तो अभी न्यूमेरिकल सबसे पहले सॉल्व करने का तरीका ये होता है कि प्रॉब्लम को पहले स्टार्टिंग टू एंडिंग पढ़ना है, उसका क्या क्या डाटा दिया है उस डाटा को कन्वर्ट करके लिखना है, so that you can able to understand what the parameters you are available. So the given data in terms of overall efficiency is indicated by efficiency of overall is 75%. If the efficiency of 75% means 0.75. The power produced, obviously the how much the power is produced at the outlet. Outlet means I told you the shaft power. Okay. So this is the shaft power is 148.25 kilowatt. In terms of kilowatt दिया हुआ है पावर. ओके. देन हेड दिया है कैपिटल एच. हेड हम नेट हेड को इंडिकेट करते हैं हमेशा कैपिटल एच से 7.62 मीटर. देन द पेरिफेरल वेलोसिटी के लिए इक्वेशन दिया हुआ है. ऑब्वियसली बोथ द वेलोसिटीज एट द इनलेट बोला है, इसलिए ये हो गया U1, राइट. और ये हो गया वेलोसिटी ऑफ द फ्लो एट द इनलेट इज VF1. तो इसके लिए इक्वेशन दिया है 0.26 इंटू अंडर रूट ऑफ 2. हमारे पास अगर h की वैल्यू अवेलेबल है, दैट इज हेड इज अवेलेबल, सो दैट यू कैन डायरेक्टली कैलकुलेट द U1 एंड VF1. ओके. यस. So all this velocity must be in the meter per second. So then only the 0.26 in the under root of 2gh. G is 9.81, h is 7.62 meter. Obviously, you should put this in terms of meter. Then only your velocity must be in meter per second. Okay. So I hope everyone is able to understand this to calculate this by your own. Okay. Use pen and paper and use your calculator to find out this value in terms of the calculation. U1 and VF1. Yes, so VFN you will get in terms of 0.96 under root of 2gh. So the G is 9.81, H is again 7.62. So you will get again the value for the velocity of the flow at the inlet is 11.738 meter per second. Now you get the both the velocities at the inlet, peripheral velocity and the velocity of the flow. Then the speed is given the in terms of capital N. It is indicated in capital N is RPM, that is revolution per minute is 150. Then hydraulic loss is available, 22% is available energy. राइट. देन द डिस्चार्ज एट द आउटलेट इज रेडियल. रेडियल जैसे ही बोला हमारे माइंड में स्ट्राइक हो जाना चाहिए कि कंडीशन है रेडियल की. आउटलेट एट द डिस्चार्ज मतलब जो बीटा है, बीटा इज द गाइड ब्लेड एंगल एट द आउटलेट इज इक्वल टू द 90 डिग्री. इफ इट इज द 90 डिग्री तो VW2 क्या हो जाएगा, 0 हो जाएगा, राइट. और VF1 VF2 इक्वल टू V2, राइट. एब्सोल्यूट वेलोसिटी इज इक्वल टू द फ्लो वेलोसिटी. तो यहाँ पे ये चीज कंडीशन चेंज हो जाएगी. जैसे ही रेडियल कंडीशन बताया वैसे ही, ओके। देन द नेक्स्ट वन, द हाउ कैन यू कैलकुलेट द इन टर्म्स ऑफ द हाइड्रोलिक इफिशियंसी। हाइड्रोलिक इफिशियंसी का हमारा फॉर्मूला हमें पता है कि हाइड्रोलिक इफिशियंसी इज नथिंग बट द आउटपुट अपॉन इनपुट, इन टर्म्स ऑफ द आउटपुट इज नथिंग बट द हाउ मच अमाउंट ऑफ द total head is achieved, right, divided by the head at the inlet. But here we have to consider the loss, right? यहाँ पे लॉस जो है वो दिया हुआ है, दैट इज 22%, द हाइड्रोलिक लॉस इज अवेलेबल, सो वी हैव टू कंसिडर दिस, so minus the total head at the inlet minus hydraulic loss divided by the head at the inlet, right? तो ये हो गया फॉर्मूला, head in terms of the capital H minus 22% of the available energy means what, 0.22 times of H, ये दिया हुआ है इन टर्म्स ऑफ, हमें इक्वेशन कंसिडर करना है क्योंकि हाइड्रोलिक लॉस अगर दिया है तो यहाँ पे हाइड्रोलिक लॉस किसमें दिया था, अवेलेबल एनर्जी में, तो अवेलेबल एनर्जी हम किससे कंसिडर कर देंगे, एट द इनलेट ऑफ द हेड, ओके। तो हेड दिया हुआ है 7.62 में, तो ये हो गया इन टर्म्स ऑफ हाइड्रोलिक लॉस ऑफ 0.22, दैट इज द 22% ऑफ अवेलेबल एनर्जी, दैट इज एच, ओके। ये फॉर्मूला बन जाएगा कैपिटल एच माइनस 0.22 टाइम्स एच अपॉन एच, बिकॉज यहाँ पे लॉस दिया था किसका, हाइड्रोलिक लॉस। अगर हाइड्रोलिक लॉस 22% ऑफ अवेलेबल एनर्जी दिया है तो अवेलेबल एनर्जी हम कंसिडर करेंगे हेड को, तो यहाँ पे हेड के फॉर्म में इक्वेशन बनेगा, तो ये हो गया आपका कैपिटल एच माइनस 0.22 टाइम्स द एच अपॉन कैपिटल एच, राइट। तो ये इक्वेशन फॉर्म अगर सॉल्व करते हैं तो 1 माइनस 0.22 इज नथिंग बट 0.78 टाइम्स एच अपॉन एच, राइट। एच की वैल्यू हमें पता है कितनी दी हुई है, 7 इन टर्म्स ऑफ 7.62, तो एच पुट करते हैं तो इक्वेशन हमें इफिशियंसी मिल जाएंगी, दैट इज द हाइड्रोलिक इफिशियंसी ऑफ 0.78, ओके। तो ये हमें पता चल गया कि हाइड्रोलिक इफिशियंसी कितनी है, 0.78 मींस हाइड्रोलिक इफिशियंसी 78%, एज सिमिलर एज फॉर द क्वाइट लेस दैन, क्वाइट ग्रेटर देन द ओवरऑल इफिशियंसी, ओके, यस। तो ये हो गया आपकी हाइड्रोलिक इफिशियंसी विद रिस्पेक्ट टू द कंसिडरिंग द लॉस, हाइड्रोलिक लॉस कंसिडर करने के साथ आपकी इफिशियंसी मिल गई। नाउ what is that formula, but now we have to find out, our first one is the अल्फा हमें निकालना है क्योंकि उन्होंने पूछा है कि गाइड ब्लेड एंगल एट द इनलेट निकालना है अल्फा। तो अल्फा के लिए मुझे क्या पता चलना है, उसके कंपोनेंट्स पता होने चाहिए, तो उसके लिए मैंने सबसे पहले वेलोसिटी ट्रायंगल ड्रॉ किया है। आपको न्यूमेरिकल में हमेशा ट्रायंगल ड्रॉ करना पड़ता था पहले भी, लेकिन अभी आपके एमसीक्यू पेपर की टेस्ट है इसलिए वो मे भी पॉसिबल है कि एमसीक्यू के लिए ट्रायंगल ड्रॉ करने की जरूरत नहीं, लेकिन मे भी हो सकता है कि असाइनमेंट 1 असाइनमेंट 2 में आपको ये ड्रॉ करना पड़े, राइट, यस। So first of all, we have to draw the velocity triangles at the reaction turbine. So as we know in the previous lecture, the same constant है ये दोनों टर्बाइन के लिए। कौन कौन से टर्बाइन, फ्रांसिस टर्बाइन और पेल्टन टर्बाइन के लिए यही डायग्राम है, हमें याद रखना है कि at the inlet triangle that will be the v1 is the absolute velocity making an angle, the guide blade angle alpha, then velocity at the blade is the u1, and that after this will be the point will be joined, that is called the relative velocity। relative velocity के साथ ही हमेशा एंगल ऑफ द व्हील का एंगल बनता है, that is the tip angle also called as the theta at the inlet, right। and then after that the absolute velocity v1 is to be get resolved by the two components vf1 and vw1, so that these two components is here vw1 and vf1, okay। at the outlet section कि हमें relative, because of absolute velocity first strike on the blade, so it will be obviously at the outlet section there will be a relative velocity first comes out। तो रिलेटिव वेलोसिटी अगर कम्स आउट होती है तो ऑब्वियसली जिसके साथ रिलेटिव वेलोसिटी है दैट इज कॉल्ड द in terms of the angle of the angle, right। so that angle at the tip is at the outlet is phi, okay। and there will be the radial flow अगर है तो वो फ्लो जो है vf1 क्या हो गया आपका 90 डिग्री हो गया बीटा, if it is the beta is 90 degree there must be a vw2 equals to 0, तो ये vf2 equals to हो गया v2, right। तो यहाँ से v2 और vf2 ज्वाइन करने के साथ अगर रिलेटिव वेलोसिटी हम ज्वाइन करते हैं इन टर्म्स ऑफ द एक्स डायरेक्शन, दैट इज कॉल्ड द पेरिफेरल वेलोसिटी ऑफ द ब्लेड, ओके, u2। तो इस तरीके से हमें ट्रायंगल डायग्राम बन गई हमारी रिएक्शन टरबाइन की। अब इसको हम यूज करेंगे कि हमें पता चल गई इफिशियंसी है, हाइड्रोलिक इफिशियंसी पता चल गई कि 70% क्यों निकाला, क्योंकि यहाँ पे लॉस दिया था, तो लॉस अगर दिया है तो लॉस कंसिडर करने के साथ साथ उसको हाइड्रोलिक इफिशियंसी ऑफ द यूज करना होगा। तो हमने हाइड्रोलिक इफिशियंसी कैलकुलेट किया, लेकिन हाइड्रोलिक इफिशियंसी के साथ साथ दूसरा हमारा फॉर्मूला है विद रिस्पेक्ट टू द वेलोसिटी ट्रायंगल, दैट vw1 u1 plus minus vw2 u2 upon gh, right। but here it is the flow is of radial, that means the vw2 becomes 0, so the only formula is that vw1 into u1 divided by g into h, okay। तो ये हमने पिछले लेक्चर में भी दिया था, देखा है, डिस्कस किया हुआ है कि फॉर्मूला कैसे मिलता है, इट इज फॉर द रेडियल कंडीशन, ओके, यस। So efficiency for the hydraulic turbine is already calculated 78%, that is 0.78. ठीक है, G पता है, H पता है, velocity at the peripheral velocity at inlet is already calculated previously. So only unknown is VW1. ओके, तो इससे क्या पता चलेगा हमें, VW1 पता चलेगा। तो इस इक्वेशन में पुट ऑल द वैल्यूज एंड गेट द आंसर बाय कैलकुलेटर टू हेल्प ऑफ VW1। you will get the VW1 at 18.34 मीटर पर सेकंड। नाउ you will get the VW1। अभी VW1 अगर मिल गया तो मुझे गाइड ब्लेड एंगल एट द इनलेट मिल सकता है। कैसे मिल सकता है? क्योंकि मुझे पता है कि tan अल्फा अगर मैं यूज करता हूँ गाइड ब्लेड एंगल कैलकुलेट करने के लिए, tan अल्फा इज इक्वल टू व्हाट, द अपोजिट अपॉन एडजेसेंट, right? The opposite is nothing but the VF1 upon adjacent is nothing but the VW1, right? So the tan alpha, you will get the value for the alpha. So the next one, our first target can be achieved. The guide blade angle, that is alpha, from the inlet velocity triangle. The tan alpha is equals to the opposite side upon adjacent side. The opposite side is VF1 upon adjacent side is the VW1. So you will just put the value for the VF1 and VW1. You will get the alpha in terms of the tan inverse of this 0.64 is nothing but the 32.619, or in terms of the 32 degree and 37, right? So you will get the tan means in terms, that is our main target first to find for the guide blade angle। ओके, तो इस तरीके से हमें पहला टारगेट हमारा कंप्लीट हो गया, टू फाइंड आउट द गाइड ब्लेड एंगल इन टर्म्स ऑफ द अल्फा। ओके, विद द हेल्प ऑफ VW1। VW1 निकालने के लिए क्या निकाला हमने? इफिशियंसी निकाली, हाइड्रोलिक इफिशियंसी। हाइड्रोलिक इफिशियंसी के लिए दो लॉस, एक लॉस दिया था और हेड के साथ दिया था, दैट विल बी द कैलकुलेटेड विद द हेल्प ऑफ द इक्वेशन, राइट? तो इससे हमें पता चल गया पहला इक्वेशन, दैट इज अल्फा। अब उसके बाद सेकंड टारगेट है टू फाइंड आउट द व्हील एंगल। what is the wheel vane angle at the inlet is theta। okay, that is also called as a tip angle। okay, wheel vane angle अगर निकालना है तो at the theta, तो again the same equation can be used with the help of the theta, tan theta, right? देखो फिर से हमें अगर यहाँ पे हमने tan theta लगा दिया तो क्या होगा? अपोजिट साइड, that is VF1 upon adjacent side VW1 minus Q1 is the rest of the part, right? यहाँ से समझ में आ रहा है सबको? अगर मैंने tan थीटा यहाँ पे अप्लाई किया तो मुझे क्या निकालना है? थीटा का एंगल निकालना है। अल्फा जैसे मैंने कैलकुलेट किया वैसे ही थीटा कैलकुलेट करना है। तो आई वांट टू कैलकुलेट द tan थीटा। आई विल अप्लाई द tan थीटा इक्वल्स टू द अपोजिट अपॉन एडजेसेंट। द अपोजिट इज नथिंग बट द VF1, एडजेसेंट मींस what the remaining part from this complete VW1 I have to minus this U1, so then only you will get the remaining part। okay, so the tan theta equals to VF1 upon VW1 minus U1। okay, so this equation will be comes out VF1 upon VW1 minus U1, or as we all know about the VF1 is what? VW1 and U1। So put all the values and you will get the answer for the theta, that theta is equals to the 37.74 डिग्री। ओके, तो यहाँ से हमें थीटा का एंगल भी मिल गया, अल्फा निकाल लिया, थीटा निकाल लिया, दो टारगेट अचीव हो गए। थर्ड टारगेट है हमारा तो डायमीटर ऑफ द व्हील एट द इनलेट। डायमीटर ऑफ द व्हील एट द इनलेट इज नथिंग बट इंडिकेटेड बाय D1। ओके, by using the relation, as we know that what is the peripheral velocity with respect to the circumference of the wheel with respect to the speed, right? So that u1 equals to pi d1 n upon 15। Circumference of the circle is pi d1, that is the diameter of the wheel at the inlet, pi d1 into n is the speed। That speed is available in terms of the revolution per minute, we have to convert it into revolution per second, because why? बिकॉज ओवर वेलोसिटी इन टर्म्स ऑफ मीटर पर सेकंड। मीटर पर सेकंड में अगर वेलोसिटी अवेलेबल है तो ये स्पीड भी किसमें कन्वर्ट करनी पड़ेगी? सेकंड में कन्वर्ट करनी पड़ेगी। तो सेकंड में कन्वर्ट करने के लिए डिवाइडेड बाय किससे करना होगा? 1 मिनट इक्वल्स टू 60 सेकंड, तो डिवाइडेड बाय सेकंड। तो हियर you will get the diameter of the wheel at the inlet, so diameter d1 equals to 60 into velocity, peripheral velocity at the inlet u1 upon pi into n। So you will just put all the values, you will get the diameter at the inlet in terms of the meter, because your velocity in terms of meter per second and diameter, so your velocity अगर मीटर में पुट किया है तो डायमीटर किसमें मिलेंगे? ऑब्वियसली मीटर में मिलेंगे। तो हियर the answer is 0.4047 meter। okay, our third target is also achieved। now the fourth and the last target, how can we find out the width of the wheel at the inlet, is indicated by V1। As we know that the overall efficiency is equals to the shaft power upon water power। So shaft power is the output for the efficiency for the Francis turbine, and the water power is the input power for the runner, obviously। So the shaft power is already available in terms of 148.25 kilowatt। So we have to find out in terms of water power। अगर water power को भी किलोवाट में निकालना है तो obviously that we have to calculate in terms of W into H upon 1000। किलोवाट में कन्वर्ट करना है तो डिवाइडेड बाय 1000 करना होगा, राइट? So that W is nothing but the weight is nothing but the rho g h, rho g q, right? So the rho GQ is nothing but the W. So here rho is the density into the that G is 9.81 into Q. Q is not the discharge, right? So the discharge as we can able to find out here, that is the unknown part. Okay, discharge हमें पता करना है, right? तो डिस्चार्ज अगर पता करना है, ओवरऑल इफिशियंसी ऑलरेडी दी है, कितनी दी थी प्रॉब्लम के स्टार्टिंग में ही उन्होंने बता दी थी, ओवरऑल इफिशियंसी कितनी है 75%. ओके, तो ओवरऑल इफिशियंसी अगर 75% है, ओवरऑल एफिशिएंसी का फॉर्मूले में ओवरऑल एफिशिएंसी हम 75% पुट करेंगे, ओनली अननोन इज दैट द डिस्चार्ज इज टर्म्स ऑफ क्यू, बाकी हेड भी पता है, राइट? ऑल द वैल्यूज यू कैन एबल टू पुट इन दिस इक्वेशन एंड द ओनली अननोन इज क्यू. क्यू हमें पता चल जाएगा, क्यू कितना मिलेगा, दैट क्यू इज इक्वल्स टू 148.25 is the in terms of the shaft power multiplied by 1000 divided by the that is nothing but the g into that is rho into g into uh, H is 7.62 into overall efficiency, that is 0.75%, so that you will get the answer for the discharge is 2.644 meter cube per second. Okay, अगर हमें डिस्चार्ज पता चल गया तो हमें पता है कि डिस्चार्ज के फॉर्मूले में ही आपका क्या आता है, इन टर्म्स ऑफ द डायमेंशंस ऑफ द in terms of the wheel, that is the pi d1 into vf1, because the discharge is nothing but the area into velocity, so that area is nothing but the pi d is the circumference of the circle for the wheel into the width, right? In terms of the v1, so the pi into d1 into v1 into velocity, that is obviously the flow velocity, because this flow velocity we have to consider for the discharge only, right? So the vf1 we have to consider the vf1 only. Okay, so this put all the values in this above equation, that discharge is already calculated into 0.644 equals to the pi into d1, the diameter is available in terms of the meter, put in 0.4047 into d1 is again the unknown value, and vf1 is again the meter per second, that is 11.738. So only unknown is that d1, that is the width of the wheel at the inlet. Okay, so you will get the width of the wheel at the inlet is 0.177 meter. In this way you will get the solution for all the unknown parameters, right? First of all, in this numerical, they want to know the inlet, that the blade angle, guide blade angle, then the vane angle, then the diameter at the inlet, and the width at the inlet. Okay, so all we have to calculate by this way. I hope everyone is able to understand this numerical for the Francis turbine. That will be the most important numerical. In the previously, this type of numerical is asking in the university exam for the 6 to 7 marks. Okay, yes, but maybe this time for your MCQs, what type of questions, such type of numericals may be asked in the MCQ type. So be prepared for that. Okay, these are the all types of the turbine runners as we are already seen. Now that the Francis turbine is already completed with the help of the first of all the Pelton turbine, then the Francis, now the Kaplan turbine. Okay, so next one is the Kaplan turbine, or called as a propeller turbine. Why it is called as a propeller turbine? The propeller turbine, the Kaplan turbine is a propeller type of the turbine which has an adjustable blade. इसलिए उसको क्या कहते हैं, propeller type of the turbine करते हैं. Propeller means you can be use the propeller at the shaft. Okay, the prop is used. What is the terms of the adjustable blade, right? So the runner of the Kaplan turbine reassemble with the propeller of the ship. This is why the Kaplan turbine is also called as a propeller turbine. The propeller turbine have the following favorable characteristics. What are the simple very favorable characteristics? The relatively the small dimensions combined with the high rotational speed, right? Yes, what is our main motto, as we are already aware, and we have seen in the previous two lectures, what is the comparison in between the impulse turbine and the reaction turbine. In that the impulse turbine, the whatever the capacity, the head is high and the flow is low, and here the in terms of the reaction turbine, the head is low and the flow is high, right? The vice versa to the each other. Okay, so here as our main target, the relatively the small dimensions combined with the high rotational speed. Okay, obviously it is submerged in the liquid, that's why it is the high rotational speed. In the large overloading the capacity, they are having the large overloading capacity, the comparatively high efficiency at the partial load, and the ability of overloading is obtained by the coordinated regulations of the guide vanes and the runner blade to obtain the optimal efficiency for the operations. That type of Kaplan turbine is also called as the axial flow turbine. Yes, how can you find out the axial flow turbine? Because this the जो भी shaft है, shaft is terms of the axial direction, and the parallel to the direction the water will be flow. That's why it is called as the axial flow reaction turbine, right? Just like the Francis turbine. Francis turbine it is a mixed type of the mixed type means what? कि रेडियली आता है और एक्चुअली जाता है, दैट इज कॉल्ड द मिक्स टाइप ऑफ द रिएक्शन टर्बाइन. बट इन टर्म्स ऑफ द कैप्लन टर्बाइन इट इज इन एक्सियल फ्लो डायरेक्शन, एक्सियल फ्लो रिएक्शन टर्बाइन. the water flows through the runner of the turbine in an axial direction. Okay, axial means parallel to the axis. Axis means जो भी shaft है उसके parallel में रहेगा. And the energy at the inlet of the turbine is the sum of kinetic and the pressure energy, right? Obviously, all the reaction turbine which is having the summation of the kinetic and the pressure energy instead of the Pelton turbine. In Pelton turbine is only the kinetic energy we have seen. Okay, yes. So this is the additional point for the kinetic energy plus total pressure energy. In an axial flow reaction turbine, the shaft is a vertical. Obviously, the vertical turbine, so that the lower end of the shaft is larger and it is known as the hub or ball. Okay, it is on this hub that the vanes are attached. If the vanes are adjustable, then it is known as the Kaplan turbine. If the vanes are non-adjustable, then this is known as the propeller turbine, just like the propeller to guide the ship, right? Yes. As we know, we have seen that the propeller in terms of the in terms of the airport, for the aircraft, right? Yes. If the vanes are fixed, then that is called the propeller turbine. If the vanes are adjustable, that means it is movable, quite movable with the certain angle. Turbine is called as a Kaplan turbine. So the Kaplan turbine have an adjustable runner blade that offer the significant advantages to give the high efficiency even in the range of partial load. And there is a little drop of inefficiency due to the head variations or the load. Okay, maybe sometimes. Yes, so you can able to see these are the three. It is the Wilton turbine is a tangential flow. Okay, the mixed type of the flow that is called the Francis turbine is the middle one. That the water is flow radially and at the exit that water will be forcefully at the axial flow, and that will be the only the axial flow. This water flow inward and outward in axial direction of the shaft. That's why it's called as the axial flow turbine or reaction turbine. Okay, yes. So these are the three diagram what I all try to tell you. Okay, yes. So the Kaplan turbine is the best suited for where the large quantity of flow of head water is available. Okay. So the Kaplan turbine is named as the V. Kaplan or called as an Australian engineer. The Kaplan turbine are now widely used throughout the वर्ल्ड इन हाई फ्लो एंड लो हेड पावर प्रोडक्शन. यहाँ पे भी हमें फ्लो ज्यादा चाहिए विद द हाई फ्लो and the low head. Low head means the height of the water flow is quite low. That means require the Kaplan turbine. The main parts of the Kaplan turbines are obviously just like the similar to the Francis turbine, the scroll casing. The scroll casing means obviously the circular casing. Then second is the guide hose mechanism. Then take the third one is the hub with vents, and the draft tube is the fourth one, which is used to release the water pressure. Okay, yes. So these are the parts of the Pelton turbine, and these are the working principle. What the working principle? The water enter the turbine through the guide vanes, which are aligned such as to give the flow in a suitable degree of thrill. The flow from the guide vane passes through the curved passage which forces the radial flow to the axial direction, right? Yes. So the axial flow of the water with the component of the swell applies force on the blade of the rotor and loses its momentum, both linear and as well as angular. So the producing the torque and rotation, obviously it will produce the torque and it will be to rotate. There is the product of power, right? पावर अगर कैलकुलेट करना है, so in terms of the torque and the rotation, the multiplication of torque into and rotation in the shaft. The scheme of the production of the hydroelectricity by the Kaplan turbine is same as that of the Francis turbine. Okay, so obviously the same working culture is available. Yes, you can able to see this is the diagram of Kaplan turbine schematic view. You can see here this will be the hub, means what the shaft is available on the shaft, that the moving vanes are adjustable. Adjustable vanes are available on the hub. That hub diameter is as large as compared to the other turbine, right? And this will be the front view. This will be the that's the propeller, okay, with the adjustable vane, and this will be the cut section of the side view, okay, when that water inlet from the penstock will be enter, and then only then the two, obviously there are also the two mechanism, guide vane and the runner vane. The two mechanism, guide vane, obviously it will be guide to the propeller vane, runner vane, right, which is to be adjustable but in the axial direction. Okay, yes. So this will be the shaft, and this will be the scroll casing with the hub. Hub is bigger as compared to the or called also called as the nose or boss. Okay. Then the draft tube, which is used to release the pressure, just like opposite to the nozzle. Okay, with with the maximum efficiency to release the water pressure and without any damages to the turbine. Okay, that will be the tail race. Tail race means the base of the section. Okay, so this will be the shaft at the section XX. So I hope everyone is able to visualize this diagram. If it is not, then again you can able to see here the what is the Kaplan turbine runner is available like this is the axis, right? This will be the shaft, and that will be the vanes, which is the moving vanes or called adjustable vanes. Okay, and that will be the hub or called as a boss. Okay, yes, the schematic view of this diagram where the water is inward in terms of the guide vanes. First of all, it will be water will be passed to the guide vanes, and then after that, the moving vanes are available at the shaft of the rotor or called as the hub or the boss. Right. With the, then after this, again the third diagram you can able to see clear your daily type of the doubts to the Kaplan turbine where the generator is used to generate the electricity, where the rotor and the starter is available to generate for with the help of the turbine generator shaft, which will be generate the electricity, which will available for the turbine blades, and the water will be flow and in terms of the actually to the axis of the shaft. Okay, so this will be the diagram, and this is the main component of the Kaplan turbine again. So the same all the diagrams are available with you people. So the scroll casing with the help of the scroll casing, and then after that the guide wheels first of all. Then after that the shaft, there will be a adjustable vanes are available at the boss. So there will be a two diameter at DB and DO. Okay, the DB is the diameter of the boss, and the DO is the diameter for the outer. That will be the runner. Okay, that you also called as a runner. Yes. So next one is the most important thing is the velocity diagram for the Kaplan turbine. As we are know that both the reaction turbine diagram for the Kaplan and the Francis are same. Velocity triangle diagram for the Kaplan turbine and the Francis turbine is same. As we know that it is a radially flow, that means the VW2 is zero. That will be the condition, and work done. If I want to find out the work done, there will be a what the work done is nothing but the rho into Q into VW1 into U1, right? Or the efficiency or the hydraulic turbine efficiency. If I want to calculate the VW2 is zero, then only the VW1 into U1 divided by the G into H is the efficiency. So here the same from what the velocity triangle diagram for the Kaplan turbine with the help of the inlet velocity triangle at the tip of the blade and the outlet where the relative velocity is only available for the making an angle, that is the angle of when in the tip angle is called phi, at the inlet is theta, then the only guide blade angle is the alpha at the inlet, only outlet the angle it is radially, that means it is actually, that's why the beta is equals to the 90 degree, right? Then only you can say that the VW2 is equals to 0. So this will be the velocity triangle diagram. Now, what will be the next working principle of the Kaplan turbine? There are some factors or called as significant properties of the Kaplan turbine, whatever the ratio in terms of the D by D ratio. What is this D by D means the capital D or called as the capital D by small d, or in terms of the dB by DO. Okay, the ratio of the hub diameter dB and the outer diameter DO of the runner. There are two diameter. Okay, just visualize this. Yes, yes, the dB is the diameter of the hub and DO is the diameter of the runner. Okay, so this will be the dB by DO is nothing but the diameter ratio. Okay, so this will be the diameter ratio dB by DO. Then next one is the what are the different second property of the Kaplan turbine is the flow ratio. How can you find out the flow ratio? कितना flow हो रहा है इसकी अगर velocity ratio अगर मुझे in terms of the flow ratio निकालना है, that is indicated by psi, and there will be ratio in terms of the VF1 is the flow velocity upon the U, that is the under root of 2GH, right? The velocity of the periphery or can called as the under root of 2GH by the head. So there will be a VF1 equals to VF2. If it is the same velocity that the flow ratio is available, then the speed ratio. What is the range of the speed ratio is 0.9 to 2.1. That is the speed. Okay. How can you find out the speed with the help of the peripheral velocity U? And that U is nothing but equals to the KU is the speed ratio into under root of 2GH. So here you please mention and concentrate that KU is the speed ratio. If I want to calculate the KU at the speed ratio, you must calculate the peripheral velocity at the whatever that the inlet or at the outlet, so that U is equals to KU into under root of 2GH. H is the head, wherever that the net head is everywhere is most important. Okay. Then last one is the discharge. How can you find out the discharge? Obviously, there are the two diameter at the so obviously the outer diameter minus inner diameter. The DO is the diameter of the runner, and the DP is the diameter um, of the hub, right? So that or called as a boss or called as a nose. So here the diameter difference, so the pi by 4 do square minus do b square into the velocity vf1. Okay, this will be the flow velocity. So in terms of this, the Kaplan turbine, there are two diameter. We have to consider the both the diameter, outer diameter minus inner diameter, or called as a diameter of the runner minus diameter of the hub. Okay, so you must calculate the discharge then only find out. Okay, yes. So here, yes, here again the u1 equals to u2 equals to the pi dn by 60. As we know that the diameter, outer diameter we have to consider because the velocity of the runner is important here, right? So whenever you want to find out the peripheral velocity, so you must calculate the pi don upon 60. Do is what? The diameter of the runner, okay, not for the hub. Please mention and please be concentrate on the two diameters are available. Don't be confused for the one diameter is for the diameter of hub and another diameter is diameter for the runner, okay, and that ratio is the dB by do. Yes. So that the velocity of the flow at the inlet and outlet are equal, obviously, because here the Vf1 equals to Vf2 or the velocity of flow, both are same. And here the area for the area of flow at the inlet is equal to area of flow of the outlet. Only the difference is what? The diameter. Both the area are equal. Only just the difference is between the pi by 4 do minus do square minus dp square. Okay. Yes. The net quantity. There are some quantities for the unit quantity. Whatever the most important thing is that see what the in order to predict the behavior of the turbine working under the varying condition of head, right? हेड वेरी हो सकता है, स्पीड वेरी हो सकती है, गेट ओपनिंग जो है आपका वो वेरी हो सकता है. The results are expressed in terms of the quantities. If I want to calculate the quantities, कितनी quantities है, unit quantity कितनी है, so that which may be obtained when the head on the turbine is reduced to the unity. Okay, so that the condition of the turbine under unit head are such that the efficiency of turbine remains unaffected. What are the different efficiencies? अगर उसको हमने यूनिट क्वांटिटी में कैलकुलेट किया या कंसीडर किया तो आपका जो भी बिहेवियरल एस्पेक्ट है वाइल वैरिंग कंडीशन ऑफ द हेड, अगर हेड वैरी हो रहा है या स्पीड वैरी हो रही है, गेट ओपनिंग अगर वैरी हो रहा है, तो इसके लिए हमें यूनिट क्वांटिटी कैलकुलेट करना पड़ेगा विच इज यूज टू unaffected the efficiency of the turbine. Okay, what are this quantity? The unit speed, the unit power and the unit discharge. Okay, three quantities है, unit speed, unit discharge and the unit power. What is this unit power? It is the speed of turbine working under the unit head. अगर unit head में हमें condition में speed calculate करनी है, so this is called as unit head. So nu is equals to the n is the rpm, whatever the rpm available for the speed of the rotor runner, right? So the whatever the speed is available in terms of the rpm, that is revolution per minute divided by the under root of head. Okay, so you can calculate the unit speed. Unit speed is the average speed. जैसे हम कहते हैं कि सपोज समझ लीजिए कि हम इनडायरेक्टली इन शॉर्ट में ये बता देता हूँ आपको कि जैसे हम एवरेज निकालते हैं बाइक का, एवरेज निकालते हैं तो एवरेज का मतलब क्या है कि आपका गाड़ी की एवरेज कितना है, राइट? इन टर्म्स ऑफ द वेरिएबल स्पीड अगर है, स्टार्टिंग में हमने 1 घंटे गाड़ी चलाई, उस 1 घंटे में आपकी स्पीड कभी 60 किलोमीटर पर आवर है, कभी 40 किलोमीटर पर आवर है, 10 किलोमीटर पर आवर है, तो उसके हिसाब से हमें एवरेज, हमारी स्पीड तो वैरी हो गई, लेकिन उसको अगर मुझे एवरेज निकालना है तो ये 1 घंटे के लिए एवरेज अगर निकालना है तो मुझे वो एक एवरेज लेनी होगी. तो दिस विल बी द यूनिट हेड कॉल्ड एज द एवरेज इनडायरेक्टली. ठीक है, तो ये एक वैसे ही डिस्चार्ज भी रहेगा, दैट द यूनिट डिस्चार्ज. इफ आई वांट टू, अगर वैरी हो रही है स्पीड 1 घंटे के लिए, फिर भी मुझे अगर यूनिट डिस्चार्ज अगर उसका कैलकुलेट करना है, एक निकालना है कि कितना एवरेज दिया है, एवरेज डिस्चार्ज फॉर दिस. So how can you find out? Obviously, that whatever the variable discharge is available, that is called the total discharge divided by the unit under root of unit head, right? So that under root of h. Similarly, for the power, unit power, it is the power developed by the turbine working under the unit head. अब इसको हमने क्या कर दिया कि यूनिट हेड को हमने फिक्स कर दिया कि जो भी आपको यूनिट हेड है उसके अंडर में जो भी फाइंड आउट होंगी स्पीड इन टर्म्स ऑफ द स्पीड और द डिस्चार्ज और द पावर, दैट कॉल्ड एज द यूनिट क्वांटिटी. ओके, यस. सिमिलरली फॉर द स्पेसिफिक स्पीड, अब हमें स्पेसिफिक स्पीड का मतलब यह है कि कितने समय के लिए एक पर्टिकुलर स्पीड, जैसे हम सोचते हैं कि वेलोसिटी एट द मीटर पर सेकंड. मीटर पर सेकंड का मतलब क्या होता है? एक सेकंड में कितने मीटर में वो स्पीड रोटेट इन टर्म्स ऑफ द वेलोसिटी अवेलेबल है, वो उसे हम कहते हैं स्पेसिफिक स्पीड, राइट? Similarly, here also the specific speed is considered in terms of the capital N suffix N, capital N suffix S. The specific speed is the speed of geometrically similar turbine working under the unit head and developed to the unit power at the maximum efficiency. Okay, so maximum efficiency के लिए जो भी हम consider करेंगे, that called the average speed or also called as the average speed. Okay, specific speed is also called as the average speed. So it is used in comparing the different types of the turbine and also using turbine section. So what are the different parameters? The specific speed, the head and the efficiency. What type of the turbine it will be available. तो यहाँ पे एक सर्वे दिया हुआ है कि टाइप ऑफ टर्बाइन कोई भी यूज होता है. जिन टाइप के टर्बाइन हमने अभी तक देखे हैं, क्विल्टन टर्बाइन, फ्रांसिस टर्बाइन, कैप्लन टर्बाइन, उसके हिसाब से उसकी स्पेसिफिक स्पीड क्या होनी चाहिए, वो स्पेसिफिक स्पीड की रेंज क्या है, उसके ऊपर से उसके हेड क्या आता है, उसकी उस टर्बाइन के लिए उसका स्पेसिफिक हेड क्या है, और उसकी यूनिट क्वांटिटी एफिशिएंसी कितनी आती है, एक एवरेज क्वांटिटी जिसे हम डिसाइड कर सकते हैं, दैट कॉल्ड एज आइडियल कंडीशन. ओके, तो ये सारी चीजें जो है वो किसके ऊपर है, आइडियल कंडीशन के ऊपर हम कंसीडर करते हैं, दैट कॉल्ड द स्पेसिफिक स्पीड. ओके, यस. तो द फर्स्ट वन इज द पेल्टन टर्बाइन. पेल्टन टर्बाइन में हमने जो डायग्राम देखी थी, जो हमने समझ के लिया था, तो वो कितने जेट के लिए था, सिर्फ सिंगल जेट के लिए हम कंसिडर करते थे. वैसे ही अगर आपके एन नंबर ऑफ जेट अगर इंक्रीज होते हैं फॉर दिस पेल्टन व्हील, एन नंबर ऑफ जेट कैन बी अवेलेबल, राइट. एक जगह से हम उसको टेंजेंशियली फ्लो अगर करना है, तो हो सकता है कि जेट हम इंक्रीज भी कर सकते हैं. उसी जगह पे हमने 2 जेट यूज कर सकते हैं, 3 जेट यूज कर सकते हैं, 4 जेट यूज सकते हैं, फोर जेट यूज कर सकते हैं, 6 जेट यूज कर सकते हैं. तो अकॉर्डिंग टू इंक्रीजिंग द जेट ऑफ द पेल्टन व्हील, that the specific speed can be increased. Obviously कि जितने number of speed jet increase करेंगे, वैसे ही उसकी speed भी increase होंगी, right. So the if it is a single jet, then 13 to 30 of the specific speed. If it is a 2 jet, then the 20 to 34 having the specific speed. If it is a 3 jet, 26 to 40. If it is a 4 jet, 32 to 47. If it is a 6 jet, the 38 to 52 is the specific speed at the whatever the Pelton wheel. As we know that whatever the head is available, that called as a specific head, is greater than 300 meter. Okay, and the efficiency, in terms of the efficiency, as we can say that the specific efficiency or the average efficiency of the Pelton turbine is nothing but the 85 to 90%. Okay, but as compared to the other turbine, what are the different parameters for the Francis and compared to the Kaplan also. So the Francis turbine, the specific speed is obviously quite maximum or quite higher than the Pelton turbine, that is for 52 to 225 speed, right. That is the specific speed. If it is the specific speed is higher, as we know that the head is quite higher, or in between the range of that from the below that the 370 मीटर, क्योंकि हमें पता है कि पेल्टन टर्बाइन का हेड ज्यादा रहता है, स्पीड कम रहती है. फ्रांसिस टर्बाइन का हेड कम रहता है, स्पीड ज्यादा रहती है. कैप्लन टर्बाइन का हेड उससे भी कम रहता है, स्पीड ज्यादा रहती है. तो दीज आर द कंपेरेटिव स्टडी फॉर द फ्रांसिस एंड द कैप्लन टर्बाइन. तो इसका मतलब क्या है कि 50 मीटर टू 370 मीटर तक ही उसका हेड बनेगा, क्योंकि वो ऑब्वियसली पेल्टन टर्बाइन से कम है. और एज कम्पेयर टू द पेल्टन टर्बाइन उसकी स्पीड क्या रहेंगी, ज्यादा रहेंगी. 52 से लेके 225 स्पेसिफिक स्पीड उसकी कन्वर्ट होंगी या इंक्रीज होंगी. And whatever the efficiency, obviously the efficiency is greater than the Pelton wheel, that is 90 to 95%, right. So the efficiency of the Pelton Francis turbine is 90 to 95%. And similarly for the Kaplan turbine, ऑब्वियसली कि सबसे ज्यादा स्पीड किसकी रहती है, कैप्लन टर्बाइन की, क्योंकि इट इज इन टर्म्स ऑफ द रिएक्शन टाइप ऑफ द एक्सियल फ्लो टर्बाइन, so that the water is directly flow inward and outward in the axial direction. So the speed of that Kaplan turbine is as compared to Francis and Pelton is high, that is 225 to 860, that is the specific speed. And obviously the जो भी speed अगर increase है, तो head हमारा कम है, obviously it is less than the 6 meter, which is comparatively less as compared to the both the two Pelton and Francis turbine. And as compared to the efficiency, so the efficiency is quite high as compared to the Francis Pelton turbine, that is 85 to 95%, right. So this is the comparative study, and again the comparison of the turbine. If I am talking about the Pelton turbine, Francis turbine, and Kaplan turbine, what are the different parameters were called as the energy at the inlet is obviously I told you the impulse energy in terms of the Francis and Kaplan turbine. It is of reaction turbine reaction energy, right. If it is a head, if I am talking about the head, what is that output for the Pelton turbine? Head is high as compared to the Francis and Kaplan turbine. So if it is the head is high as in terms as for the Pelton, it is medium for the Francis, and it is low for the Kaplan turbine. Similarly, the flow direction, as we know that the flow direction for the Pelton turbine is tangential. The flow direction for the Francis turbine is mixed. Mixed means what? The radially entry and axially outlet. And in terms of the Kaplan turbine, it is completely axial direction, inlet to outlet. It is completely the axial flow. Okay. The next point, what is the discuss about the discharge required? What is the required discharge is low. Here for the Pelton turbine, Francis turbine, the medium discharge is required or it is available, and the Kaplan turbine it is high discharge. highest discharge, obviously the high speed and the high discharge will be available in terms of the Pelton turbine. As compared to the Pelton and Francis turbine, the discharge is high, and obviously the specific speed. Okay, so similarly for the specific speed for the Pelton turbine is low as compared to the Francis turbine. It is medium and it is the high in terms of the high for the Kaplan turbine. So this will be the comparison for the all the three types of the turbine: Pelton, Francis, and the Kaplan for the energy, head, flow direction, discharge required, and the specific speed. Okay. Yes. So in this next lecture, we will start the numerical for the Kaplan turbine, because this is the most important concept for the Kaplan turbine. Also, similarly for the previous lecture and for the today's lecture, we have conducted the numericals for the Francis turbine and the inward flow, outward flow reaction turbine. Okay, the radial flow in the turbine. So I hope everyone is able to understand this type of today's lecture, right? You can take the screenshot of what this and try to solve this numerical at your home. Okay. Yes, thank you. So I hope everyone is able to understand what the concept is available with us. Then only we will definitely try to solve this numerical, then only. Okay. Yes. So now it's time to take your attendance, as why I'm taking this why I'm taking that shorten this lecture, because I hope most of the students not able to give the attendance, and